Hey guys, my name is Gabe, and today we'll be talking about Ohm's law and the minimum square method. So Roshni made these slides, and Francisco helped us revise and edit both the script and the PowerPoint. So if you see him in the hall, make sure to say hi, and thank you. Okay, so what is Ohm's law? So Ohm's law is the relationship between voltage, current, and resistance. So in other words, it is V is equal to IR. So voltage, or volts, is equal to current times resistance. So this is used everywhere from, your phones to your laptops. Really anything that requires an electrical output will use voltage, current, and resistance. So in your advanced labs, if you're in engineering or physics or really any other type of STEM major, when you do your advanced labs, you're going to be using pretty advanced scientific equipment. And so really all the readings, everything that you will see, are based off of three things: the voltage, the current, and the resistance. Okay, so let's jump into the conceptual side of Ohm's law. So what is voltage, what is current, and what is resistance? So voltage is basically the potential difference between 2 points on a circuit. So if we draw a circuit right here, we have this point, let's just make a square, right? Okay, so if we have all of these different points, and let's say that this is a battery. Well, I'm sorry that this is bad, but so let's say that this is just a regular circuit. This may not be a good circuit, but it's just for demonstration. So let's change the color. So we have a battery right here, and we have just different wires connecting all together. So it's just a regular circuit. So the potential difference can be at this point and this point, or we can measure it from this point to this point, or really any different combination. It's just the measurement that we can make. Hopefully that makes sense. Okay, so now moving on to current. So current is the flow of electrons, or it's the flow of charge. So in the same example, what we have is that we have this battery, and we have our different points in the circuit, and so current is just the way that the electricity flows. You can really think of it as water too. So I guess, yeah, in a sense, let's think of everything as water. So in a sense, water flows through, and it flows in just one direction. So current is the way, or the characterization of the way that the water flows, or the electrons flow. And resistance, or let's go to resistance, and resistance is just the measure of opposition to the flow of electrons. Okay, so let's elaborate on this water example just for a second. So let's think of a hose that we use to like water our plants or our backyard. So in this example, we can think of water as electricity itself, and we need to get water out of the hose. And in order to do that, we need two things: one, pressure, and two, flow. So in order to shoot water out of the hose, we need a kind of pressure that makes water move. And this pressure is the same thing as voltage. So right here, it's the raw power behind how much electricity will flow outwards, so out of the hose. So in the same manner, water goes outwards and hits the end of the hose. But let's get to the second part, the flow part. So in this sense, the flow is limited to how wide the opening is. So in this sense, it's the diameter. So it's how it regulates how fast the water moves. Okay, so now let's go to resistance, or I guess the opposition to the flow. So resistance affects the flow, but in the way that it impedes the output, as we said before. Instead of having, a perfect column of water, now we get other stuff like, sand or dirt. It impedes the perfect flow or the perfect column of water from going out. So the same principle can be applied to electricity. So it acts as a sort of limiter. So now the electricity is impeded as a function of resistance in the system. Okay, so all of these quantities basically work in conjunction with each other, and hence we have Ohm's law, or voltage, V, is equal to IR, or current times resistance. So this next slide might be a little confusing, but hopefully I'll be able to explain it pretty well. Okay, so this slide is all about the mathematics of Ohm's law. So here we can see the different relationships in Ohm's law. So we have V is equal to IR, as we've talked about before. We have I is equal to V over R, and we have R is equal to V over I. So some people find that this triangle helps in distinguishing these relationships. We're going, across the triangle, like IR is multiplication, and going up and down is division. I'm not sure if this makes sense, so let's go over it again. So in this case, I is equal to V over R. You see that V is up and down, so V is vertically. V and R is, like vertical. And in this case, or in that case, it was division. So in this case, the next part, going across is multiplication. So you have V is equal to I times R. So I've always found that this triangle is a little confusing. So another method of finding these quantities is just to do simple algebra. So you start off with V equals IR, and then depending on what you want, say you want current, or say you want resistance. So depending on what you want, you can solve for it. So either method is valid, but if you have a hard time visualizing the triangle, the algebra solution might be a little bit better for conceptualization. So now let's go to the lab section. So in this lab, you'll be using resistors. And so resistors have certain color coding on its base to help you identify what kind of resistance is on the part. So as you can see here, there are a bunch of different colors that you can have. So you can have black, brown, red, orange, yellow, and everything else. So the importance of all of this is how to read it. Okay, so this can get a little complicated. So bear with me here. Okay, so the resistors have certain bands, and these bands correlate to different things. Okay, so the first band and the second band indicate the number of significant digits. The third band is the multiplication factor, and the fourth band represents the tolerance. Okay, so this is a little confusing, so let's do one together. Okay, so let's see. Right here. Okay, so our example. So let's just go with the answer first. So we know that the answer is 2 times 10 to the 5th plus or minus 10%. Okay, so let's do it step by step. Okay, so we have the first band. So the first two bands, remember, are the number of significant figures. So the first band, black, is 0, and that's what goes to this. So that's why there's a 0 right here. Okay, now if we go to the second band is also the number of significant figures. So if we can see right here, the second band is number 2. So the second figure, number 2, the second band. And that is why we have 2. Okay, so now when we move to the third band, we have the third band right here, which is the multiplication factor. So the multiplication factor is, as we have right here, the times 10 to the 5th. So that means that the multiplication factor is multiplied by the first two significant digits that we have. Okay, so now once we have this, we have something called we have the fourth band, and that's something called the tolerance. So the tolerance is 10%, and we find that because the fourth band is silver. So we go to this fourth band column, and we go all the way down to where it's the color, and we have plus or minus 10%. So that's how we read this chart. That's how I read this chart. So now that we know how to read it, I need to talk about tolerance. So tolerance, in a sense, is the error between the range of values that the resistor can go. So in this example, the 10% tolerance means that the values can be anywhere from 2.2 times 10 to the 5th and 1.8 times 10 to the 5th. So it's an error of 10% in the part itself. So one thing that you might see if you take any kind of advanced labs is a resistor with 5 bands. So these are basically only present in really high quality resistors. But it's the same as what we talked about before. The last 2 bands are for the multiplier and the tolerance, and the first 3 bands are for the significant figures. So the more bands we have, the smaller and smaller the tolerance becomes. Okay, so now that we've talked about how Ohm's law works and all of the concepts behind it, we now need to take another look at how we can apply all of this knowledge in a different sense. Okay, so remember the first slide when I was talking about power and how heat kind of relates to electricity and Ohm's law? So this is the explanation on all of that. So this is something called joule heat. So while we have Ohm's law that describes electrical interactions, one of the most important parts of physics is actually putting everything that we know into different uses. So one of these uses is power. So as we talked about, electric power is the rate at which work can be done in a circuit, and that's equal to the voltage times the current. So P is equal to VI. Okay, so when we go back to the conceptual description of everything we had before, we could think of this as the work that water can do, and that's equal to the pressure and the flow rate. Remember the 1 and 2. So because we have the raw strength of voltage and the opening of the hose, or the allotment of flow, both of these together is the change of work. Okay, so in another sense, this mathematical description can also be seen with respect to the current as well. So in this case, we have P is equal to I squared times R. So this is called Ohm's power law, which you'll see if you take really any advanced labs that have to do with heat at all. So we always have like the correlation between electricity and power and how that relates to heat. So the units for power is actually given in a different quantity we call watts, or W. So watts can be represented in a bunch of different, subsections. So watts is equal to joules over the second, which is also the volts times the amps, which is also the resistance times the current squared. Okay, so in this, it's basically the ability to do work in the form of heat. So when we talk about all this, we can see that the relationships between watts is always correlated to what we talked about before, Ohm's law. So in the case of this lab, we need to think of the application of heat and resistors. Because of the heat, we need to make resistors out of different materials, such as metal film, which usually uses blue coating, carbon film, which usually uses brown coating, and any other different material. So why do we use different materials? So these materials all have different heat transfer coefficients. Those of you who will be taking your engineering heat transfer course later will learn more about this. But what this means is basically that different materials disperse heat either better or worse, and it's because of the atomic structure of the material itself. Now we completely switch gears to pure math and the start of statistical analysis. So in this case, we'll be talking about the minimum square method. So, the minimum square method is just a fancy word for the line of best fit. So the line of best fit is a statistical tool that is used to characterize a bunch of data, and it finds a function that closely resembles it, so we can later recreate the mathematical representation and also manipulate it to get useful traits out of it. Okay, so when talking about this minimum square method, we can see that it's basically just the equation of a line, y is equal to mx plus b, where m is the slope, or the change of y over the change in x, and b is the y-intercept. So, or, the value of y when x equals 0. Okay, so one important note is the characterization of this equation. So this is a first degree polynomial, and so we can see this by looking at the power of x. If we look at x, it has nothing to its power, which by algebraic rules characterizes this as the first degree polynomial. And so the same goes with second and third degrees too. And the degree is just a fancy word for the highest power in the equation. So if we had a second degree polynomial, we would see x squared. If we had a third degree polynomial, we would see x cubed. Okay, so now that we've talked about the minimum square method, let's see what it actually does. So here we can see the graphical representation of what is happening. So we have a lot of different data points that don't line up, but we can see that there's a general trend that the line goes in, and that is called the regression line, or as we said before, the line of best fit, which is really just y is equal to mx plus b. So this is what the minimum square method does. It finds a line based off of the points that we are given. So we're given just a lot of different data points that don't exactly match up, but we're able to get just a general trend. Now that we know the theory behind the minimum square method and sort of a visualization of how to implement this, we now need to look at the mathematics behind it. So when we have data points, we have something called deviations or errors. And so these errors are in between 2 points. And let's see. So like, for example, between this point and this point. So these errors are used as a basis for finding the line of best fit. So we characterize this by saying delta yi is equal to yi minus m times xi plus b. So this basically means that the change of yi, or the observed response, is a function of the slope, the observed value, and the y-intercept. So this can be found by writing down all of the individual points and then applying the formula that we talked about before. One extra point to talk about in the minimum square method is the use of negative values. Okay, so if we go into the math a bit more, which I won't go into extremely deeply, we say that square deviations are used to avoid positive and negative values canceling each other out. So we say this because in physics we want an equation to be applicable in a variety of different possible situations. So to do this, we make sure to account for a lot of different possibilities, and this is one of them. So all of this that we see here is just a look behind the curtain that helps us use this method for a broader sense of possibilities. So if you have more questions on this or want to go deeper into it, I would highly suggest either asking your professor or asking the TA. So while the minimum square method is great and versatile for a lot of different situations, it's not without its limitations. So one of them is that this is only good for 2 dimensions, x and y. So if we have data in the z direction, this doesn't really account for it at all, which really makes it only usable for data sets where x and y are present. So another thing is that this method is really only reliable when data points are more or less evenly distributed. So when there's a very large deviation in the points between each other, the formulation that we saw in the previous slide doesn't really hold. So this also ties into outliers too, which again skew the analysis dramatically. So while the minimum square method is great for a lot of different applications, it's not infallible, and it really just shows that for more complicated data analysis, we need to use different methods that are better suited and more tailored to your situation. So now let's talk about the lab. So throughout this entire PowerPoint presentation, we've talked about both the minimum square method and Ohm's law. So now what we need to do is we need to combine both of these. So in this experiment, we combine both of these ideas, and so we say that V, or voltage, is the dependent variable, right here. V is the dependent variable, and current is the independent variable. So, in a sense, we can say that the slope m is actually equal to the resistance, and that is given by the change of voltage over the change in current. So in this experiment, you're going to combine all of these concepts through the use of resistors, and basically how to use scientific equipment to get our data. In the lab, you'll be using 3 different types of equipment: the ammeter, the voltmeter, and the ohm meter. So all of these measure current, voltage, and resistance. So for measuring the current, the ammeter must be connected in series with the object, and for measuring voltage, the voltmeter must be connected in parallel to the object. While measuring resistance, it just needs to be connected to the object. With the power, and you have to make sure that the power source is disconnected, because if you don't have it disconnected, you will blow the fuse on the ammeter. Okay, so now let's go into these words that you might or might not know: series and parallel. So these traits are basically a splitter in the way that the current flows. So in a series circuit, right here, all elements are arranged in just a single path. So current can just go straight through. But when we get to parallel, the current is split into different paths. So the current has multiple paths to flow through. So let's go back to our water example. So with a series circuit, we can think of water just going into the system just straight in and out. So it's only slowed down a little, as there's only one path that the water needs to flow through. But while in parallel, the water will split into 2 or more hoses for voltage. Okay, so now this last point. We put this at the end because this is a little bit advanced and a little bit confusing. So one important thing in this lab that you'll see is the statistical measure that represents an inherent variance in the formulation itself. Okay, so that's a lot of words. So remember when we talked about the square deviations? This is sort of the same idea. So there is an inherent error in the formulation that we made, and it just so happens that in this case we characterize this as r squared. So r squared is a statistical measure that represents the portion of the variance in both y and x. Okay, so this means that if the r squared value is 0, the model is not a good fit for our data. But if r squared value is 1, it means that the model we use is a very good fit for our data. So for linear expressions, a higher value of r squared indicates a lot better fit between the model and the observed data, while the acceptable tolerance is then dependent on us. So it's basically what we interpret to consider acceptable or not. So in a sense, for linear models, a good representation for r squared needs to be accompanied by a graph. Okay, so for example, let's say that we have a sine function. So a sine function looks like, or let's just say a sine or a cosine function. It's just an oscillating function. So it looks like this. So in this, we just see regular oscillation. It doesn't have any kind of linear behavior. And that's because 50% is up here. Oh wow, yellow is not a good color. Okay, so because 50% is up here, and then 50% is down there. So this predicts only the direction that the wave is traveling, and not the behavior of the wave itself. So when graphing this statistical measure, you have to be careful that what you are graphing makes sense conceptually with what you're trying to find. Okay, so recap. So r squared is just a statistical measure that represents the portion of variance. So it represents the error or the variation in between 2 different points. Okay. And so one thing that we do have to go over is how to create a graph in Excel. So this is fairly simple. So you just select your data and then go to charts, where you then choose a scatter plot and add a linear trend line. So more detail will be provided in the lab handout. So depending on what version of Excel you have, the location of the graph will be different. And if that's the case, you just need to look for the Functions tab. So I do know that it is fairly easy to look up on the Microsoft website. So if you look up your specific version of Excel, it should have a very easy flowchart to follow. And so yeah, so this has been Ohm's law and the minimum square method, and until next time.